Okay, good morning. Welcome to this day on the subject of risk and odds ratios, logistic regression and survival analysis. And the common factor here is that we have a dichotomous outcome variable. Outcome variable, dependent variable with only two values, 0 or 1. So I put together content like this, talk about risk and odds ratios, logistic regression, and then survival analysis with a focus on Cox regression here. I guess that's the most commonly used survival analysis, although there are others. So risk and odds, what are those? Risk, same as probability, frequency of individuals with outcome divided by total frequency, can vary between 0 and 1. 0, nobody has outcome. 1, everybody has outcome. 0, and so on. Odds, instead of frequency of individuals with outcome divided by those without, the frequency of individuals without outcome. So it could be said that odds is a ratio of probabilities. And the odds can vary between 0 and infinity. That's one of the reasons we sometimes prefer it before risk. So let's have a few examples. Imagine we have a group of 10 individuals. So in this first case, 2 of them are sick and 8 are healthy. So what is the risk of being sick in that group? 20%. And the odds of being sick? It's 0.25, 1/4. So I guess risk is nothing strange for you. Odds could be seen as I just said, a ratio of probabilities, a ratio of risks. So this 1/4 says that the probability of sick is 1/4 of the probably not being sick. So it's 4 times more common to be healthy than to be sick. That's what the odds ratio there says. If we have 5 sick and 5 healthy individuals, the risk of being sick, 50%, and the odds of being sick, 1, exactly. So the probability of being sick and not sick is the same. That's what the odds ratio there, odds tells us. And in the last example, 8 sick and 2 healthy. Risk of being sick, 80%. Odds of being sick, 4. So the probability of being sick is 4 times higher than the probability of not being sick. So that's the difference between risk and odds. And then you can wonder when somebody says that the odds for something is high. The odds of Malta winning the World Cup in football is I don't know if they're in there any. But if they would be, the odds, somebody might say, oh, it's a very high odds. It's a hög oddsare, as we say in Swedish. Then you, of course, say, no, I would think the odds is very low for them to win. Because high odds means high probability, not the opposite.
You cannot use risk there, no?
Yes, of course. We can always go from risk to odds with those formulas. The risk is odds divided by 1 plus odds. And odds is the risk divided by 1 minus risk. So, of course, they have a perfect association. So, if we calculate the risk ratio, risk for outcome in one group related to divided by the risk for outcome in another group. So let's say we have 2 groups here. those who abuse drugs or alcohol or something, they abuse, and one group who don't abuse. So in our example here, we have 250 individuals, 173 of them abuse, and 77 don't abuse. And then some of them have dementia and others don't have dementia. 165 have dementia and 85 don't have dementia. I don't know what kind of sample this would be with those values, but let's imagine we have a sample with this combination of values. So we ask for the risk for dementia if the person has abused compared with not abused. How does abusing affect the risk of dementia? So the risk of dementia if you have abused, 122 divided by 173, so 70.5%. And the risk for dementia if you have not abused, 43 divided by 77. That is 55.8%. And then we take the ratio of those two risks, and we get the risk ratio of 1.263. So there is an association between abuse and an increased risk for dementia. For an individual who have abused, the risk for dementia is 26.3% higher compared with a person who has not abused. Of course, usually we're not only interested in saying how it looks like in our sample. We want to estimate how would it look like in the population that the sample is representing. So we want to do some kind of significance test of this. What do you think is the null hypothesis?
There is no difference between those who abuse or not abuse.
Exactly. There is no difference in risk between the two groups. There's no difference in risk for outcome between the two groups in the population. What would that mean when it comes to the risk ratio? That means that the risk ratio in the population is 1. The risk is equally high in both groups. So the risk ratio is 1. So we try to what we test is if our calculated risk ratio differs significantly from 1. That's what we test. If it does not differ significantly from 1, we say we can't with enough confidence say that the risk ratio in the population would be something else than 1. Therefore, we so far assume that there is no difference in risk between the two populations, the two groups. If our risk ratio, on the other hand, differs significantly from 1, then we say we can with enough confidence reject the null hypothesis. Therefore, we claim that in the population there is an association between which group you belong to and the risk for outcome. That's what we say. So in order to significance test our risk ratio, what do we want? Not only the point estimate, not only the risk ratio in our sample. What do we always calculate when we try to significance test something? Variance, yeah, kind of. Standard error, exactly. What was that now again? I forgot during the weekend here. I watched too much Bolibompa this weekend, so I have forgotten what standard error is. No, what is it? What is a standard error? It's an estimation of something. Estimation of how much, on average, parameter values calculated in a sample differ from the parameter value in the population. An estimation of that. Average difference between parameter values calculated in samples and the parameter value in the population that the samples are representing.
Parameter values
Mean is one parameter value. Regression coefficient might be the parameter value. Right now, we calculating risk ratios. So whatever we are calculating. So in this case, risk ratios. So the risk ratio in our sample was 1.263. So we have a formula here for a standard error of the risk ratio. Or actually, this is not the standard error of the risk ratio. It's the standard error of the natural logarithm of the risk ratio. So we have a formula. P1, percentage with outcome. In our case, dementia in exposed group. And in our case, exposed group is those who have abused. P0, percentage with outcome, dementia, in non-exposed group, not abused. And then we have number of exposed, those who have abused, frequency of those, and number of non-exposed. We put in the values there, and we get the standard error of the natural logarithm of the risk ratio, 0.113. Of course, we could calculate the t-value of this, but we could also, I follow the Spss's output here, we could calculate 95% confidence interval. So because this is we take the natural logarithm of our risk ratio. So we take the natural logarithm of that, 1.263, plus minus 1.96 multiplied with the standard error. Why 1.96? Zeta. 5% of the distribution. Exactly. In the zeta distribution, 95% of the values are between minus 1.96 and plus 1.96. So 95% of the distribution is between those values. It means that with 95% confidence, a parameter value calculated in sample will differ maximally 1.96 standard errors from the parameter value in the population. The risk ratio, if you have, it's like this. If you imagine you have a population and you have some kind of risk ratio in the population, and you draw samples from that population, and you calculate the risk ratios in the samples, the distribution of those risk ratios calculated in samples is not normally distributed. We transform it in order to get at least more normally distributed values, and then we can use the zeta scores, the zeta table, in order to calculate the significance of this. And one of the reasons it doesn't become normally distributed is that the risk ratio can never be below 0. It cannot be negative. So imagine you have a risk ratio in the population, 0.1. You will never get in a sample a value that is below 0. So you tend to get a positive skew in the distribution of risk ratios calculated in samples. And in order to make it more normally distributed, we use the natural logarithm of that instead.
For what degree of freedom do you have this 1.96?
No, we don't have degrees of freedom in this calculation. So it's not as, I would guess, it's not as exact like when we use the t-table. Then we take this into consideration. Here we don't. We would use this 1.96 independently of how large the sample is.
But if you use to t-test, for example,
how could we make a Yes, of course. It wouldn't be, we might call it a zeta value instead of a t value. How would we calculate the zeta value from these values here? How do you get the zeta value? The same way as the t value. You take your parameter value, you parameter estimate. What do you do with it? Divide it by standard error. So in this case, we would take the natural logarithm of 1.263 and divide it by 0.113. Then we would get how much the natural logarithm of our risk ratio calculated in the sample, how many standard errors it differs from 0. And in that case, we would compare with 0. And you might think it sounds a bit strange because this null hypothesis is that the risk ratio in the population, not that it is 0, but that is 1. But what is the natural logarithm of 1? I don't know if you know that, but it's 0. So if the risk ratio in the population is 1, it means that the natural logarithm of the risk ratio in the population is 0. So if we do this by the way of natural logarithm, we would compare with the value 0. And we could go do a zeta test like that. So we would see if our calculated zeta value, if we did like that, was outside of the range plus minus 1.96. And if it is, then our risk ratio in the sample differs significantly from 1. But if I follow the Spss output, because they present confidence intervals for this instead, so we could calculate the confidence interval by taking the natural logarithm of our risk ratio calculated in the sample plus minus 1.96 standard errors. In this case, those values. So if I use the minus here, I take that value minus this, and then e raised to this, and I get the value 1.012. If I use the plus there instead, and then I take e raised to this, I get the value 1.575.
Unlogged.
Unlogged, exactly, because we take e raised to this. Then we get back to the, not to the risk ratios, instead of the natural logarithm of the risk ratios.
Do you know, is it significant?
Is it significant?
Differ from 1, but I mean, what is p value? How can we calculate?
Oh, we can calculate that. We don't know exactly what it is here, but we know it's so the p-value is less than 5%. So how do we interpret this confidence interval we get here?
Very wide, very marginally different from the
Yes.
1.
Yes, but still.
Not significant.
Yes, but still, how do we interpret this? With 95% probability, the risk ratio in the population is within this range. And because 1 is not within this range, we can reject the null hypothesis that the risk ratio in the population would be 1. So we say in the population there is an association between abuse and the risk for dementia. In the population, those who have abused have a higher risk for dementia compared with those who have not abused. In the population, the increase in risk, if you abuse, is somewhere between 1.2 and 57.5% higher compared with if you don't abuse. That's the interpretation. Odds ratio. formula there. But as I said before, so the odds is frequency of individuals with outcome divided by frequency of individuals without outcome. So if you want to calculate the odds ratio here, so we calculate the odds for having dementia if you have abused. That would be 122 divided by 51. 2.4. Among those who have abused, the odds for having dementia is 2.4. It means that the probability of having dementia is 2.4 times higher than the probability of not having dementia among those who have abused.
If you ask the non-dementia versus dementia, then odds ratio will be less than 1, right?
Yes. Then it would be 51 divided by 122, which would be exactly the same as 1 divided by 2.4. So if you want to go in the other direction, you take the inverse. Yes. If you want to calculate the odds for not having dementia, then you take 1 divided by this, then you get that odds ratio. It's the same as the inverse of this odds ratio. Okay, if you calculate the same odds among those who have not abused, then we take 43 divided by 34. 1.265. So among those who have not abused, the probability of having dementia is 26.5% higher than the probability of not having dementia. And now, if we have the odds in the two respective groups, we take the ratio of them and get 1.9. So there is a 90% increase in the odds for dementia among those who have abused compared with those who have not abused. That's what it says. Of course, we again don't want to just say what the odds ratio is in our sample. We want to calculate what it might be in the population. So we want to calculate the standard error for the odds ratio. But then again, this formula doesn't give the standard error of the odds ratio. It gives the standard error of the natural logarithm of the odds ratio. Okay, in this case 0.284. And in order to calculate the 95% confidence interval, we do it the same way as before. If you use the minus here, and then e raised to this, we get 1.084. If we use the plus here, e raised to this, then we get 3.3. What we do is we estimate the probability of getting odds ratio that differs this much from 1 or more if the odds ratio in the population actually is 1. So if the null hypothesis is correct, the odds ratio in the population is 1. What is the probability of, in a sample of this size, get an odds ratio that differs this much or more from 1? We calculate that probability. And because our confidence interval here doesn't include the value 1, we say that probability is lower than 5%. Therefore, we reject the null hypothesis.
But we don't say more than that, because I never seen any p-value in the odds ratio calculation. That's why you always do the confidence interval.
Yeah, but we can calculate the p-value for this also with the Mantel-Hansel, whatever it was called. We'll have a look at it soon. Maybe the next slide, actually. exactly. Mantel-Hansel common odds ratio estimate. So this is for the exact same data. We get a p-value here of 0.025. So we see it's lower than 5%. The probability of getting odds ratio that differs this much from 1, if it would be 1 in the population, is 2.5%. So it's lower than 5%. Therefore, we reject the null hypothesis. I guess it's the zeta distribution. I'm not completely sure, but that is mine. Because that's what we use for the calculation of the confidence interval. Because those are two sides of the same coin. So I guess it's the zeta distribution here. But we see it calculates the natural logarithm of our odds ratio. And the standard error of the logarithm of the odds ratio. That's what have been used. We get, in SPSs, we get output like this. We calculated those. It does like this. It calculates, because risk ratios might become different depending on what direction you look at here. Well, not in this case. So this is the risk for not having dementia. So the risk of not having dementia in the first row compared with the second row. So in this case, the risk of not having dementia among those who have not abused compared with those who have abused. So the risk of not having dementia is 50% higher among those who have not abused compared with those who have abused. And that confidence interval does not include 1. So we conclude the risk or the probability of not getting dementia in the population is higher among those who do not abuse compared with those who abuse. And this is the risk for having dementia in the first row compared with the second row. And there the risk ratio becomes below 1. And it differs significantly from 1, because 1 is not in the confidence interval here. That is one of the nice things with odds ratios. So if you have two outcomes, for instance, you have dementia and you have, heart disease, and you want to see if there's an association between those. Which one will you use as the outcome? Which one will you use as the exposure variable? If you calculate odds ratio, it doesn't matter. The odds becomes exactly the same, independently of what direction you look at. While the risk ratio is affected by this, it does not become the same if you look in different directions. And of course, sometimes, we see this as an association. We have two outcomes, we want to see an association between those. So it feels quite natural that the result becomes the same independently of in what direction you have a look at it. In the same way as a correlation. Okay, now we come to logistic regression, and I'm going to talk about binary logistic regression with a dichotomous outcome variable. So it's for only two possible values on the outcome variable. There are other versions of logistic regression also.
The binary is same with dichotomous?
Yes. Binary is the same.
No.
Yes, no. Or,
Same.
Binary, that's how it's called in SPSs. And what we're doing again, actually, is we're predicting the natural logarithm of the odds ratios to have the value 1 on the dichotomous outcome variable rather than the value 0. If you call the values on the outcome as 1 and 2 instead, well, don't. Well, it tells you which it uses. It recodes the values. So the outcome is given the value 1, and the non-outcome is given the value 0. And why don't we use ordinary linear regression? Ordinary least squares linear regression, as it's called, which we came across last week. Why don't we use that instead? Well, it could be used. It's not completely useless, but we might get strange results. So here is weight, and this is real data. Weight in kilos. Okay, and here is sex. 0 for women and 1 for men. So we predict sex from weight. Nice, right? Nice fit. Do we have something here that we don't like? What is that difference there called? Residual. It's not a very nice fit here. And if we use this linear regression line, as is often done in regression, to make predictions. If a person weighs 70 kilos, what would we predict? If you weigh 70 kilos, we predict that your sex is 0.5. So you're somewhere between a woman and a man. You're half-half. That's our prediction. If you weigh 110 kilos, God, you're masculine. You're even more of a man than all the men here. And so on. So we get unreasonable predictions. If I do that, I use this as an ordinary linear variable. I get values like this. And we get the regression weight here 0.018, 0.02. Actually, it's not completely useless. This tells us that the probability of being a man increases by 2% or 2% points for every increase in weight with 2 kilos. With 1 kilo. So that's what it says. But then, of course, it might give us strange predictions. If you put in a value of 110, for instance, I guess it would say that the probability of you being a man is more than 100%.
But the regression line looks still okay, right?
Yeah, this is the optimal regression. Yes. I fitted. This is what we would get. This is the optimal regression. But it feels a bit strange to do. Predict outcome on a dichotomous variable. Well, you can only have either value 0 or 1 to get up to predictions that is outside of those two values. So we won't predict values on the outcome 0 or 1. What are we going to predict with logistic regression? We are predicting the odds of being a man. That's what we're going to predict, depending on your weight. And of course, we will get a value that varies between 0 and infinity, and it's nothing strange with that. So let's have a look. So I group them into different groups here according to weight, and then we calculate the odds of being a man in different weight categories, and it looks like this. So the odds of being a man among those who have very low weight is very low, and then it increases a bit. Among the heaviest here, the odds of being a man is very high. Let's see here, for instance. Among those who weigh between 100 and 104 kilos, well, let's say it's about 20. The odds of being a man is about 20. What does that mean?
10 times higher odds of being man in
Yes. The odds of being a man, no, the probability of me being a man, if you weigh between 100 and 104 kilos, is 20 times higher than the probability of being a woman. That's what it says. If we try to fit a regression line to these data, will it fit nicely? No. So what will we have here instead of odds of being a man? The natural log of the odds of being a man. Let's have a look. It's so nice. Do you see? They are very nicely fitted on a straight line here. It's a very strong association between weight and the natural logarithm of the odds of being a man.
But if you use only logarithmic scale then instead of linear in the first upper one,
yes?
how would it look?
How does it
Look.
Well, we could fit a exponential curve here. But if we take, of course, if you have an exponential association, but instead of the original values on the outcome variable, you take the natural logarithm of those values, the exponential association becomes a linear association. And then we can fit the regression line to these data. And the relationship between variables are quite often exponential. For instance.
What's wrong with that?
No, nothing wrong. Nothing wrong. We don't mind that. But in order to fit a straight regression line to this, here, for instance, let's say it's 0 there among those who weigh between 70 and 74 kilos. It's not exactly 0, but let's say it's 0. What does that mean? The natural logarithm of the odds of being a man among those who weigh between 70 and 74 kilos is 0. What would that mean? What would, in that case, the odds of being a man in that weight group be? If the natural logarithm is 0, the odds is 1. So the odds, the probability of being a man or a woman is the same among those who weigh between 70 and 74 kilos. The frequency of men and women is the same in that weight category.
So it doesn't matter if you have 500 men weighing 70 to 74 or 200 women. Would affect the results. I'm not really.
If it would affect the results, yes, yes.
What are you looking for? 70 to 74, for example.
Of course, the absolute frequency. If you have much more men in your
affect those ratios.
Yes, but it wouldn't affect the effect of your predictor on the odds, because that's what we're calculating. It would affect the intercept in your model. The baseline odds of being a man is affected of how many men you have in your sample. But it doesn't affect the regression coefficient you're going to get in your analysis. Because the effect of an increase in weight on the odds of being a man is independent of the frequency of men and women in your datasets. So the absolute frequencies affect the intercept, but not the regression coefficient. So I have a Spss output here for logistic regression. Looks like this. And what we get, even without asking for it, we get step 0. It's called a null model. So it's a model with no predictors. So in this case, we're predicting the probability, the odds of being a man, and this is the null model. It only contains an intercept. So we could have a look here. We have exponential value of the intercept that is 0.9. So what this null model does, it predicts that the odds of being a man is 0.9 for everyone. It's the same for everyone in the dataset. Odds of being a man is 0.9. How does it come up with that value? Why not 0.4? Why 0.9? What does it get that value from?
Is it just based on prevalence of men and women?
Yes, exactly. That is the odds of being a man in this dataset. So there is slightly less men than women in this dataset. So the odds of being a man is 0.9. So in this null model, it predicts that is the odds of being a man for everybody. If we take the natural logarithm of that value, we get the value here. Minus 0.105. We get the p-value for it also. Might not be much of an interest. In this case, it's not significant. If we would like to, what kind of conclusion would we draw from that? In the population that the sample is representing, the distribution of men and women. No, the opposite. Our distribution here does not differ significantly from 50-50. So it could be equal amount of men and women in the population. That's what it says. Okay, so that's a null model. Now we include our predictor. In this case, weight. So now we take into consideration each person's weight. What happens? We get a value like this. I'll talk a little more about that in a moment. -2 log likelihood. It's an estimation of non-fit. How bad our model is at making predictions. The likelihood value here stands for, we could calculate that, the probability of getting our data if that would be the intercept and that would be the regression coefficient in the population. If those are the true parameter values in the population, what is the probability of getting our data? Okay, that's what the likelihood stands for. So the higher the better. And it can vary between 0 and 1. Now we take the logarithm, the natural logarithm of that likelihood. Log likelihood. And if we take a logarithm, natural logarithm of a value that varies between 0 and 1, then it can vary between 0 and minus infinity. And the higher the value, the closer it is to 0, the better fit between data. No, the higher the probability of getting our data if those would be the true parameter values in the population. And now we multiply that value with -2. Because the logarithm is negative, we multiply it with -2, it becomes positive. And the higher this -2 log likelihood is, the worse is the fit. The lower is the probability of getting our data if those were the true parameter values in the population. So -2 log likelihood is a measurement of misfit. The higher the value, the worse our model is at making predictions. But we can't just have a look at it and say, oh, it's a bad fit or good fit, because it's affected by sample size. The bigger our sample is, the higher this value becomes. But what we can do is to compare. If we have the same sample and calculate two models in that sample, we can compare the two models -2 log likelihood values. Which of the models fit better to data? In this case, it says that the minus 2 log likelihood value of our model with weight as predictor is 277.3. This table here says that the minus 2 log likelihood value has decreased with 67.2 from the null model. So by adding weight as a predictor into the model, the minus 2 log likelihood value decreases with 67.2. From whatever it was in the null model to 277.3. Okay. What do we lose in our model compared with the null model? Do we lose something? Well, in our model, we calculate one extra parameter. In the null model, we only had an intercept. Now we have an intercept and a regression coefficient for the effect of weight. So now we calculate 2 parameters instead of 1. We lose, on the model level, we lose 1 degree of freedom. That's what that value stands for. We lose 1 degree of freedom. Then the question is it worth to sacrifice that 1 degree of freedom in order to get a better fit between data and the model? Well, the nice thing, that's why you calculate minus 2 log likelihood. The nice thing with minus 2 log likelihood is that it has a chi-square distribution. And the nice thing with chi-square distribution, that even difference between 2 chi-square values have also a chi-square distribution. So now we can calculate a p-value here. A model with 1 extra parameter, but where the minus 2 log likelihood decreases with 67.2, is significantly better at predicting values on the dependent variable. So our model with 1 predictor, with weight as predictor, is significantly better at predicting the odds of being a man compared with the null model. So it indicates it's worth sacrificing that 1 degree of freedom. The model's minus 2 log likelihood value becomes significantly lower. It says here also that it's an omnibus test. What is an omnibus test? When we do ANOVA, the ANOVA is an omnibus test. When we do regression analysis, multiple regression analysis, we also get an ANOVA table. That ANOVA is also an omnibus test. How did we interpret a significant value in the ANOVA table when we conducted a multiple regression? How did we interpret that significant F ratio when we conducted multiple regression analysis? Explain variance. We interpret it that the explained variance in the population is higher than 0. R square, amount percentage explained variance in the population, can be assumed to be higher than 0. That's what a significant F ratio when we conduct a multiple regression is interpreted as. But we interpret it as an omnibus test also. And because the R square in the population can be assumed to be higher than 0, at least one of the predictors have an association with the outcome variable in the population. Not all regression coefficients can be assumed to be 0. It's the same here. If this is significant, we say the model becomes significantly better at predicting the odds for outcome by adding those predictors. At least one of them has a regression coefficient that is different from 0 in the population. Of course, in this case, we have only added one predictor. So it's not difficult to guess which it is that is significant. But we might have added several predictors. Then this says that at least one of them has an association with the odds for outcome in the population. And then we have a look at this table in order to see which one it is. So here we have so to speak, a regression table with our parameter values. We have an intercept, -7. Can compare it with what we had in the null model. It's much lower now. So what we say here, the natural logarithm of the odds of being a man is given by the formula 0.1.3 times weight in kilos, because that's what we used, minus the intercept 7.221. What does the intercept mean? What does the intercept mean in regression analysis? Yes, what did you say there? Yes, it's when weight is 0, the odds of being a man. Can odds be -7? No. So it's not the odds of being a man. The natural logarithm. The natural logarithm of the odds of being a man, if you weigh 0 kilos, is predicted to be -7. If we want to have it in odds instead of the natural logarithm of odds, what do we do with that value? We take e raised to this. Look how nice we have it here. So if we take e raised to this, we get that value. So what does it say? It says that the odds of being a man if you weigh 0 kilos is really, really low. So most of those who weigh 0 kilos are women. That's our prediction here. Of course, it's not sensible. How about these regression coefficients for the effect of weight? 0.103. If, how do we interpret regression coefficients? If weight increases by 1 kilo, because that's the unit we're using here. If weight increases by 1 kilo, what happens?
Also increase.
Yes, the odds of being a man increases. If you want to be more exact and use this specific number, 0.103. If weight increases by 1 kilo, the natural logarithm of being a man increases with 0.103. If we take e raised to this, we get this value. E raised. E upphöjt till. The natural value raised to this. Exactly, we unlog it. Then we get this value. And what does this mean? We have it in odds instead. But it's no longer an additive scale. It's a multiplicative scale. So this value tells us if weight increases by 1 kilo, the odds of being a man increases by 10.9%. So for every increase in the predictor with 1, in this case, weight increases by 1, we multiply the odds with 1.109 in order to get the new odds. And if we multiply with this value, it's the same as it increases by 10.9%. If the predictor has no association with the odds for outcome, what value do we get here? There's no association whatsoever. Then we get to 0 here, right? The regression line is flat. There's no association. If we take e or anything else raised to 0, we get 1. It means that if the predictor increases by 1, we multiply the odds with 1, which means that we don't do anything with it. It remains the same. If there's a positive association between the predictor and the odds for outcome, then this value, as in our case, is positive, and this value becomes higher than 1. It means that the odds for outcome increases when the predictor increases. If there's a negative association, then this is negative, and this one is below 1. But this one never becomes negative. If it's below 1, if it will be 0.8, for instance, it means that we multiply, if the predictor increases by 1, we multiply the odds with 0.8, which means that we decrease the odds by 20%. If it's 0.8, did I say like that? If it's 0.8, it means we multiply with 0.8, and that is the same thing as decreasing the odds with 20%. So if we have our formula there. So if we would calculate the odds of being a man for various weights, we put in the values in the formula there. So if weight is 70 kilos, for instance, then we get that the natural logarithm of the odds of being a man is minus 0.011. E raised to this, odds of being a man, 0.989. And odds, we can recalculate the probabilities if we want. So if you weigh 70 kilos, the probability of you being a man is calculated as 49.7%. 80 kilos, 73.5%. And so on. We don't get any nonsensical predictions anymore, because we're not predicting what value you have on the variable sex on the scale from 0 to 1. We are instead predicting odds, or if we prefer, we can recalculate those two probabilities.
But we said decrease or increase in the previous slide.
Yes?
If it's under the 1, so odds here 0.98, 0.99.
Yes?
Under 1.
It's under 1.
So it means decrease or increase?
No. That was the effect of weight. What happens with the odds when the predictor increases by 1? Here is the calculated odds for a specific value on the predictor. In this case, 70 kilos. Yes?
And if someone wants to calculate the diagnostic value of this model, comparing to the 0 and 1 that we have in our observed database,
Yes?
then is it like if this calculation is less than 50%, we'll consider it as 0, or is it higher than 50%? I mean,
If you want...
finally change our prediction to 0 and 1.
Okay, you want, for instance, predict if a person has is a case or non-case.
Yeah.
Exactly. Yeah. If the predicted odds is higher than 1, it's a case, which means the probability is higher than 50%. The predicted odds less than 1, non-case.
And can we ask Spss to write this or to add a column?
we get information. Yes, you mean a new column? Yeah, yes. We can get the predicted values, and of course that we can easily recalculate to 0 or 1 by saying if it's higher than a certain value, you get a 1. If it's lower than a certain value, you get a 0. So I put this in yesterday. So this is the mathematical rule. The difference between, we have a that's what the natural logarithm is all about. That's why he used the natural logarithm. If you have two values, a and b, and we take the natural logarithm of those, and take the difference between them, okay, that is the same thing as taking the natural logarithm of the ratio. It's a mathematical rule. That's how it works. That's how universe works. If we unlogarithm, which you use, good expression, if we unlogarithm this side by taking e raised to this, then it would be the same as unlogarithmize this side. And e raised to this is the same as the ratio between the two values. In this case, in our example, if weight increases by 1 kilo, the natural logarithm of the odds of being man increases by 0.103. So, if you take a person with weight plus 1 kilo, take his or her odds of being a man, natural logarithm of that, and then minus the same thing for somebody who weighs 1 kilo less, then the difference between those two natural logarithm of odds, natural logarithm of odds is called logit. That's what it is. So if we take the difference between the logit of those two individuals, it's 1.013 according to this calculation. And because we have this relation, the ratio, the natural logarithm of the ratio of those two persons' odds of being a man is the same thing according to this rule here. And therefore, if we unlog this value, okay, it's the same of the ratio, it's the same as the ratio between their odds of being a man. So if a person weighs 1 kilo more than another one, according to this, the odds that he or she will be a man is 10.9% higher. We're no longer using sum of squares, and so to speak, when we do the calculation. Instead, when we use this, we use something called maximum likelihood estimation. And it's a popular way of calculating. Next week, when we talk about structural equation modeling and multi-level modeling, the estimation of parameter values, intercepts, when I say parameter values, from now on, I mainly mean intercept and regression coefficients. But parameter values could also be means. Well, it's whatever we are calculating. So maximum likelihood. Okay, so what this does that for various combination of parameter values, it calculates the likelihood of getting our data if that would be the true combination of parameter values in the population that the sample is representing. So it tries out different combinations, and the result it presents for us is the combination of parameter values that gives the maximum likelihood. no other combination of parameter values will give a higher probability of getting our data if they were the true parameter values in the population. So the likelihood function is this one, and what maximum likelihood does, it maximizes that. Let's have an example. So it's the same data we've been using. I have various individuals here. We have their weight in kilos, and we have their sex, woman or man. And this is the result the maximum likelihood estimation came up with. So what we can do now is that putting in the person's weight in this formula, we can calculate the probability for this person to be a man or a woman according to this formula. So on the first line here, we have a person who weighs 61 kilos. According to our formula, if you weigh 61 kilos, the probability of you being a man is 28%. The probability of you being a woman would be the rest, 72%. And here I have probability actual. So in this case, this person is a woman. And the probability of her being a woman, according to this calculation, is 72%. So here it says 72%. The probability of her actually be having the sex she has, according to our calculation. What kind of values do we want to have in this column here? P actual. We want to have near 1, high values. Because that means our formula is good at predicting the person's sex. And we see we have quite high values here, with a few exceptions here. We see here we have a man who weighs 95 kilos. If you weigh 95 kilos, the probability of you being a man, according to our formula, 93%. And it is a man, so 93%, no problem. But in the line before him, there's another person who weighs 95 kilos. But this is a woman. So those values are exactly the same because they weigh the same. But because this is a woman, the P actual here is only 7%. So, given that this would be... So how do we calculate the likelihood? The probability of getting a data set that looks like this, and in this case, the probability of getting a data set where people weigh this much in combination with their sex. How do we get the probability of getting our data if these are the true parameter values in the population? How do you get the probability of several independent outcomes? We have the probability for each case. So what do we do with these values? We multiply them with each other. What is the probability if you throw a coin to get heads, and then you throw a dice and get 4? What is the probability of that? Getting heads and a 4. How would we calculate that?
Multiply.
Yeah, 0.5 multiplied with 1/6. It's the same here. So the probability of getting a data set where people have these weights and this sex, then we take 0.7 multiplied by 0.8 multiplied and so on. How will that value get, do you think? In our case, it becomes 4.4 multiplied with 10 raised to minus 64. So 0.00063 zeros and then a 4. That is the probability of getting this data set where people have these weights and these sex if those are the true parameter values in the population. The likelihood, this probability, is really, really, really low. But it doesn't get better than that. That's maximum likelihood. If we try different combinations here. So I tried different combinations of intercepts. So these are different possible intercepts and different coefficients for the effector weight. So here we have the one we actually got, the intercept and the regression coefficient. 4.4 times 10 raised to minus 64. It never gets higher than that. We have an intercept of 0.1.3 and a regression coefficient. No, here's the intercept, minus 7.221 and a regression coefficient 0.103. Maximum likelihood. It's very low likelihood, but it's maximum likelihood. We have another peak here, a secondary peak, that might work quite well, but not as well as our peak. So that's maximum likelihood estimation. We try different combinations, or we don't do it, but the program does. It tries the different combinations of parameter values and calculates the likelihood of getting our data if that would be the true combination in the population. And it presents to us the combination of parameter values that has maximum likelihood. The highest probability of giving us the data we actually have. We can conduct multiple logistic regression with several predictors, just like we did with ordinary least squares, linear regression. Okay, so in this case, I add 4 different predictors: age, height, weight, and how many times the person have been subjected to physical violence. Okay, that's what it stands for. I asked the subject. So 4 predictors. What happens with the model with those 4 predictors compared with the null model? Significantly better. What do you base that claim on? What do we lose from the null model? 4 degrees of freedom, because we're going to calculate 4 regression coefficients, so 4 extra things, so we lose 4 degrees of freedom. 174, what does it stand for?
Log of likelihood.
Minus 2 log likelihood. Do we like minus 2 log likelihood? Is it one of our friends, or is it a friend or a foe? Foe. We want it to be as low as possible.
How low could be? Is it decrease?
Well, 0, but you never get 0. That would mean you make perfect predictions. So we compare with the null model. The minus 2 log likelihood decreases with 174 when we add those 4 predictors. So we lose 4 degrees of freedom, but we gain a decrease in minus 2 log likelihood. And that is a significant decrease. So our model becomes significantly better. Its minus 2 log likelihood value is significantly lower compared with the null model. How do we also interpret this? It says omnibus up there. What does it mean? We have added 4 predictors. Yes, at least one of the coefficients for the 4 predictors, at least one of them have a coefficient that is different than 0 in the population. At least one of them has an association with the outcome variable. In this case, with the odds of being a man. Of course, when you do linear regression, we want to have as high R square as possible, because it means that our model is good as explaining variance in the outcome variable. We can't calculate R square in the same way as in logistic regression, but we get something that's called pseudo R square. So it tries to calculate something similar to R square in regression analysis. So we have one, Cox and Snell, and another one, Nagelkerke. That's what Norwegians want to say, but he was Dutch, so I don't know. Cox and Snell has one slight disadvantage. It can never be 1. So it's negatively biased. And Nagelkerke compensates for that, for the negative bias. So Nagelkerke will always be at least as high as Cox and Snell. I guess due to this, maybe Nagelkerke is the better one of these, because it compensates for the negative bias Cox and Snell has. So what does this mean? The Nagelkerke R square 0.69. What does it mean? 69% of the variance in the odds of being a man can be explained by these 4 predictors. Exactly. That's what it says. So it sounds like a quite high number. A lot of the variance in the odds of being a man can be explained by this. Before, weight had a highly significant association with the odds of being a man. And I haven't changed the data. I only added 3 more predictors here. What do we see now for the effect, for the association between weight and the odds of being a man? It's no more significant. Isn't that strange? Why isn't the association between weight and the odds of being a man, why is it no longer significant? What is the difference between regression coefficients in a multiple regression and simple regression? All other variables, all other predictors are kept constant if you express it like this. So if we keep age, height, and subjection to violence, if we keep those constant, what kind of association does weight have with the odds of being a man? If you keep those constant, for every increase in weight by 1 kilo, what happens with the odds of being a man? It increases by 3.1%. And before it was 10.9, if I remember. So the association, the strength of the association have decreased. What could be the main culprit for that decrease in the association in this example? Is there some of the 3 other predictors that might have made the association between weight and the odds of being a man much lower? Height, exactly. Because height and weight, of course, have strong association. So if we adjust for height, the association between weight and something else, well, we can guess that it quite often becomes much weaker. So in this case, weight, so to speak, overshadows the association between weight and the odds of being a man. So how do we interpret? We see here the p-value for the coefficient of weight is very significant. So what does the association between height and also being man look like? And height is in centimeters. For every, or when height increases by 1 centimeter, what happens? The odds of being a man increases 34%. Given that the 3 other predictors are kept constant. Yes.
So is it correct to write that this relationship is adjusted for other variables?
Yes, that's.
Plate is keeping constant to adjustment.
It's the same thing. It's quite often expressed as adjusted. You calculate an adjusted effect. You have an adjusted model and so on. It's quite often expressed like that. It's the same as keeping everything else constant. And of course, I think I more and more say that because it's more specific of what it means to adjust. You keep everything else constant. Is there any age difference between men and women in my data set? Yes? Which group is younger? Which sex is younger in my data set? What kind of association do we have between age and sex? For every increase in age by 1 year, the odds of being a man decreases 7%. Exactly. Given that everything else is given kept constant. So the men are younger. Exactly. They're slightly younger in my data set. So survival analysis. When do we use this? Okay, so we have combination of 2 variables. We have a dichotomous outcome, has a certain event that we're interested in. Has it occurred or not? So 0 or 1, yes or no. However, if it has happened, the event has happened, then we also have information about when did it happen. How long time did it take for the event to happen? So we have longitudinal data. We have a follow-up period during which the event might occur. For some individuals it occurs, for others it doesn't. But then of course for those for whom the event occurs, it takes different time for them to experience the event. And usually we have some censoring in our data, which we'll have a look at just in a second. If we use logistic regression for this, then we would only predict, did the event occur, yes or no? But we would not take into consideration how long time it took for the event to occur. Of course, from the name here, survival analysis, we might guess what the event has quite often been that we're trying to predict. Death. So we have a follow-up period. During that period, some subjects die, others don't. And if they die, some of them die earlier and others later. So survival here means that the event does not occur. So if you don't die, you survive. But then again, we might have patients who are all ill. And we try to predict if they get healthy or not. So in that case, the survival would mean that they don't get well. They continue being sick. And the event would be that they get healthy. So survival could be something positive or something negative. Survival means no change. So let's have a small example here. We have 25 individuals. They have differing values on emotional control here. Okay, and then during a follow-up period, they either die with the 1 here, or they survive with the 0. And those who die, they die at different time points. So the full time period here, follow-up period, is 450. Let's say it's 450 days, for instance. So those who survive all have value 450 here. And those who die have different values, depending on how many days it took for them to die from the start of the follow-up period. So if we would conduct a logistic regression, so we predict death or not from emotional control. And we compare it with Cox regression, which is probably the most common survival analysis, where we also take into consideration how many days did it take for those who died to die. Then we get these results. Logistic regression, emotional control has no effect whatsoever. Because I made it here, for every level of emotional control, there are 5 individuals, of which 3 die and 2 survive. And it's the same. No effect of emotional control on the odds of dying. With Cox regression, although it's not significant, at least we get some kind of effect here. It's not completely zero, the effect. We have some effect here. Why do we have an effect in Cox regression here when there is no effect at all in logistic regression? Because although the odds of dying during the follow-up period is the same for every level of emotional control, the higher your value in emotional control, the longer time it takes you to die if you die. So although the odds are the same, we get an effect here. Although the odds are the same, the hazard is different. That's what we calculate with Cox regression. Not the odds for outcome, instead the hazard for outcome. And I'll have a word about that soon. We quite often have some kind of censoring in our data. And there's 4 different kinds of censoring. So this is called uncensored data. So here 0, that's where the risk period starts, the follow-up period starts. And here we have data for 1 individual. We know when he or she enters the follow-up period, so we know the starting time here. And we also know when the event of interest occurred. Here the person, in our case, the event is death in cancer. Here the person died in cancer. So uncensored data. The start of the risk period is known as well as the time of event. The second example here, it's called right censored data. We have a person, we know when his or hers follow-up period started here, but we don't know when the event occurred. Maybe because it has not occurred yet. The person is still alive. So right censored data. Left censored data. For an individual, we don't know when the follow-up period, the risk period started. That's called left censored data. And the last example here, random censoring. We have a person, we know when his or her risk period starts, and we know when it ends. But it ends not because due to the event, but due to something else. So if we, for instance, want to predict death in cancer, and all our subjects or patients with cancer. Of course, it might happen that a person stops being under the risk of dying from cancer, but not because they died from cancer. Maybe because they died in a car crash, for instance. So if you die in a car crash, you will never die in cancer. It's a perfect cure. So the risk period ends, but not due to the event happening. What we don't like is this kind of left censoring data. The other three types we can manage, but this is more difficult. But of course, it might be, we have to make a decision. When does the risk period start? Imagine, for instance, we're going to predict if patients die in cancer or not. When does the risk period start? There are a few possibilities. When does the period for the risk of dying in cancer, when does it start? So some kind of diagnosis or date of diagnosis?
Time of diagnosis is not necessarily the time when the wrong things started.
So you have a diagnosis, but you try to predict back in time when the changes start?
Time of diagnosis.
Yeah, that might be one. But let's say we want to make a study, so we contact a lot of cancer patients, and we ask them, when did you get your diagnosis? Okay, is there something problematic with that? Using that as the start of the risk period. Well, actually, if they had died before we contact them, they would not be in our sample, right? So we could say, well, the risk period starts now, because if they died before now, they would not be in our sample. So we could say, although they had got their diagnosis further back in time, the risk period starts now. I'm not saying one of them is right, the other one is wrong, but
Can you get retrospective? Retrospective.
yeah, maybe. Yes. We add a patient, although he or she died already.
All journals.
We have data from journals and so on. Yeah. Yes. Yeah. What I'm saying, you have to make a decision. When did the risk period start? What are we going to use as the starting point here? Sometimes you see, well, the risk of dying starts when you're born, so we use that as the starting point. It depends. So if I have an example here, I use the diagnosis as the starting point here. So we have a number of patients here. What date did they get the diagnosis? And the end of our follow-up period is here. That's when we stop. That's when we conduct our analysis. We don't take into consideration whatever happened after that date. During this period, some of these patients died. 1, those died. 0, they're still alive. And for those who died, we get the date of death. So we can calculate this time variable here. And it will be number of days in this case from diagnosis until death for those who have died. Time under risk. After they have died, the risk period ends. And for those who have not died, the time variable gives the number of days from the diagnosis until the end of the follow-up period. So the time states gives two different values, depending on if the event has occurred or not. If somebody of these persons moved to another country or something like that, so we can't know anything more about them, then we might have date here. When we missed this person, lose track of him or her. So we calculate the time from the diagnosis until we lose the track of them. Okay, and event would be 0 here.
But we don't know the outcome.
No, we don't know the outcome. But it's the same. We don't know the outcome for these other patients either. They might die. They might die the next week. The only thing we know is that they have not died of cancer during this period. But it's the same for those who disappear. We know they didn't die of cancer during that period.
Is it better to exclude them from study?
No. As a general answer, I would say no. We can still use the information that they survived until we lose track of them. It's a shorter period, of course, because we don't have the full period. If we wait long enough, what would analysis do we do then? If we predict all-cause mortality from something, and we wait long enough, everybody dies. So then you don't predict like this if they die or not. What do you predict? Age of death. What analysis do you use then? Linear regression, because then you have a linear outcome variable. How old were they when they died? So we're doing analysis like this. We have conscription data. Almost all Swedish men born between 49 and 51. Okay. So sometimes I say our data is getting better and better. They die more and more. More and more of them die. If you wait 50 years, then we have perfect data. And we don't have to use Cox regression anymore. Then we can use ordinary linear regression. Yeah. Okay. Yes.
Is there any rule of thumb or number of necessary events that we need to have?
I guess there are some. I haven't come across those. I don't present any here.
For example, if in a specific period of time we have only one death out of 200 or 100.
Yeah. Sounds much too small. Of course, what happens if you have a few events? What happens? What changes in your analysis?
Confidence interval.
The confidence interval. The standard error becomes larger the fewer events you have. So of course it will affect your results. The result becomes more robust, smaller standard error. The larger the more individuals have the outcome. These survival analyses, there are a few of them. They can be either parametric or non-parametric. Non-parametric, no assumptions about the form of the survival function in the population. Okay, two you can find in SPSS, life tables and Kaplan-Meier. So robust test, they don't make any assumptions. Parametric methods, you make an assumption about how the survival function looks like in the population. Okay, so it could be that you assume the survival function looks like this. So we have time here and survival. So you might assume it looks like this in the population. Or you might assume it looks like this in the population. Or it looks like this. So you define how you assume that the survival function looks like in the population. Okay, we won't do that. Then we have our favorite here, Cox regression. Semi-parametric method. It makes no assumption about the survival function, how it looks like in the population. However, it makes an assumption that the survival functions look the same in groups that we are comparing with each other. So if we, for instance, are going to compare the survival of men and women, we make the assumption that the survival function looks the same among men and women in the population. Yes, we're going to have a visual look at it in a similar way as we did with regression analysis. Okay, life tables, you can get these in SPSS. Have you ever come across one of these in a paper? You have? I have never. No. Well, I guess it feels like more of a descriptive. You want to describe how the survival looks like during a period. So here we have it divides the time period, the full time period in this case. I guess you can change that into 10 equally spaced time periods. And we could, for instance, plot that against proportion surviving. So in the beginning here, okay, they all survive, then they start slowly to die here, and then it increases. So the survival decreases a lot in the end of the time period. Kaplan-Meier. Okay, it also divides into different time periods. But the time periods go from one event to the next. So let's say the time period starts, the follow-up period starts after 3,554 days, something happened. Don't mind, it's simulated data, so it's strange values here. Something happened. And this indicates the event occurred in one person. So for instance, one person died after 3,500 days. And then it goes another time period, and then after 5,331 days, something happens. But it's not an event. So it might, for instance, be that somebody moves to another country and they disappear from our data set. And so on. What you can do with this Kaplan-Meier is that you can compare the survival between different groups and see if it's significantly different. So in this example, let's assume that the green line here is for men and the blue line is for... No, the green line is for women and the blue line is for men. So we have survival time here, the time period starts there, ends there, and proportion surviving. I guess they might look much more interesting than this. So what Kaplan-Meier here can do is to compare the survival between those two groups. And with various, we can get various significance tests of those. In this case, all three of these say it's a significant difference in survival. Women survive to a higher degree than men during this time period.
You look all three tests or mental Cox, like Cox and around there.
Yeah, they calculate the difference in. They have different algorithms.
Is always all of them significant or not?
No. I guess usually.
This one you must prefer the law, whatever.
Then you choose the one that says whatever you want to say. Well, in this case, if you look at the chi-square here, it's not much difference. Maybe this Tarot where is a compromise between those two. Yeah, I think I read something, some recommendation. I can't remember which one.
Is it something on crossing of the survival curve?
Yes.
If they cross somewhere.
If they cross somewhere, first one group has higher survival than the other one. Of course, survival goes down, but let's say they cross somewhere. Then looked at over the full time period. There's no difference in survival between the two groups. But what you might miss that there is a time by group interaction. So survival in one group is higher during early days, in the beginning of the time period, and survival in the other group is higher in the latter part of the time period. So you might miss something interesting there. Of course, you probably see that if you plot them and have a look. But if you only have a look at this data and it says it's non-significant, you might miss that kind of result. Okay, we come to Cox regression. Cox proportional hazard model, as it's called. Survival function, we don't need to know exactly, we don't make any assumptions about how the survival function looks like in the populations. Okay, however, the ratio of hazards is assumed to be the same. So if we're going to compare the hazard of death between men and women, for instance, we make an assumption that the ratio of that hazard is the same over the full time period. So, which would mean that the survival lines, survival curves, they are parallel during the time period. For instance, that they don't cross each other; they are parallel. The parameter values are affected by the rank of survival times, but not their absolute values. So, if in one group, if we rank the survival time, if one group the rank is lower than the other one, we might find the parameter value. It's the ranking remains the same, although we change the absolute differences in survival time, doesn't affect our results. So it's non-parametric in that sense. It treats the survival time as an ordinal scale variable. Cox regression allows inclusion of predictors that change over time. So I don't know. Do you have any favorite? Well, in my examples, I'm using systolic blood pressure as predictor of death. So if we have a patient group and we measure their systolic blood pressure on several occasions during the follow-up time, then it changes. Within individual, the measured value of blood pressure changes. We can include that in our model. That would mean we use the latest measured value on systolic blood pressure as the predictor of hazard for death, rather than the measured value at the baseline. So we use more of the information. Okay, what is hazard? It's a conditional probability. So if I have a line here, so this is time. And let's call this point in time t. And this point we call t plus delta t. Okay? A little bit later. So what hazard is a proportional probability. What is the probability for the event to have happened by that time point, given that it has not occurred at this time point? So if death is our event, what is the probability that the person will have died here, given that they have survived until then? What we compare is hazard between groups, or due to what value you have on a continuous predictor. What the algorithm does, it treats this as how do you call it, limit. So it calculates the probability of to have died at this time point, given that you have survived until that time point, when dt moves towards 0. So imagine the following. We have a timeline here, and we have the same timeline here. And both of these persons die. One of them die here. And one of them die here. So, of course, the probability of them dying during this follow-up period is the same. They both die. The odds is the same. They both die. But is the hazard for them dying the same? For which of these two individuals is the hazard of dying higher?
Second one.
Yes, because this person died earlier. It survived less of those time periods, so to speak. So although two individuals die, the earlier during the time period a person dies, the higher his or her hazard of dying is. So if we compare, we're never going to say this about individuals, but if we compare the hazard of dying between men and women, for instance, if they die with the same frequency, 50% of them die, but men tend to die earlier during the follow-up period than women do, then the hazard for dying is higher among men compared with women.
So what practically you can use that? If your intervention with a therapy, for example, you can prolong the hazard that time.
Yes,
compared to not treated.
Exactly. If your treatment is effective, it prolongs the survival time, then it decreases the hazard of dying. Although they still might be dying, of course we all will die, but the longer we live, the lower is the probability of dying during a certain time period. Therefore, the hazard of dying is lower, the longer you live. So this is sometimes interpreted as speed of change. High hazard, change occurs quickly. And if change is you go from being alive to dead, high hazard means you die with a faster speed. Death rate per time unit sometimes. That is the formula. It's, well, I don't understand a thing about this. But, what we say is called partial likelihood. And what we don't get, compared with other regression analysis we conducted so far, we don't get any intercept. So it's always only comparing the hazard of event between groups or between levels of a certain predictor. We don't get an intercept. Okay, if we have data like this, we have a number of individuals, emotional control, intelligence. Okay, I think this might be from our true data, conscription data. So we have measured intelligence at the conscription on a Stanine scale. So 9s are the really smart ones with high intelligence. And then we have if they have died, and latest I had a look at this was if they had died by 2008, if I remember right. Okay, so if they have died or not. And if they have died at what date. And then we have survival time here. So we see, for instance, this person dies young. Only, this is not true data, I see it here, but 573 days after conscription, this person dies. While this person also dies, but at a much later date, in 2003 instead of in 1970. Okay, so data might look like that. And if we do a Cox regression on this, we get output like this. Okay, we have a null model without predictors. And we have -2 log likelihood for that model. Now we add a predictor, in this case only one, intelligence. what happens with the models. If you add a predictor, how bad it can, no matter how bad it is, what will happen with a model's -2 log likelihood? It will decrease. Because of course, even with a bad predictor, you can explain some of the variation in the outcome. So it decreases. How much does it decrease? Well, in this case, it decreases from that value, 65,971. Sounds like a huge number, right? Why do you think it's so large number here in -2 log likelihood? Yes, we have a very huge sample here. It's 49,321 individuals here. And imagine you multiplied all those values. And of course, the larger your sample, because you're always multiplying with something that is less than 1, the more data you have, the lower is the log likelihood. The lower is the likelihood, the higher is the -2 log likelihood. So we don't really care about its absolute value here. But that's what the null model has. Now we add intelligence as a predictor, and it decreases from 65,971 to 65,747. So it decreases by 224. What do we sacrifice by adding intelligence as a predictor compared with the null model? 1 degree of freedom. Is it worth that sacrifice? Yes. A chi-square value of 224 with 1 degree freedom is significant beyond imagination. On 5% level, the limit is 3.84 for a chi-square value. So this is very significant. How do we interpret that? A model with intelligence as predictor is significantly better at predicting the hazard for death compared with a model with no predictors. We get our regression table, so to speak. As you see, we have no intercept. However, we have a coefficient for intelligence here. Could you guess what that stands for? That's one of the reasons why this fits quite well with logistic regression. What does the regression coefficient here stand for? When? Exactly. It's a natural logarithm of the hazard. Exactly. So when intelligence increases with 1 on this scale from 1 to 9, what happens? The natural logarithm of the hazard to die decreases by 0.30 or 12.2%. How do we get that value? How do we get that value? E raised to minus 0.30. So for every increase in intelligence with 1 on this scale from 1 to 9, the hazard for death decreases by 12.2%. Yes, 12.2%. In the same way as we would do in logistic regression. But now we change the word odds to hazard instead. And if you want, we get 95% confidence interval there. Okay, this is called cognitive epidemiology. Intelligence is good for many things. It's good for income.
Not to worry.
It's good for marriage. If you want to get married, that is. Explains a few things about me, I guess. And It's good for getting old. Survival. It's good for health. Here, diagnostics. It's called proportional hazard. So in this case, we have 9 levels of intelligence. We calculate the effect of intelligence on the hazard for death. Because it's proportional, the relationship, the ratio between the hazard, between the different levels of intelligence, is assumed to be the same over the full time period. And we can check for that by having a look at something called a log minus log plot. And don't ask me exactly what it is. I tried to look it up. I guess if we put some time into it, we could figure out exactly what the values stand for. But if we have log minus log here, log minus log for the event, and we have survival time here, what this assumption about proportionality says, that these lines should be parallel. They should not cross each other, they should be parallel. So in this case, well, after a certain time period, it really fulfills that. They look perfectly parallel, these lines. What I've seen, they usually look like this from the beginning, but it's not that. We want them to look parallel here.
I don't understand the difference between these two.
Now this is survival. Then you take the log of that somehow, and then you take some other log minus log, and you get to that. I tried to figure out how we get from these values to these values. Of course, they're related, but here the ratio is multiplicative. So this is the same ratio, although the difference between them increases. But that ratio, that similarity in ratio becomes that they are parallel here, that the distance remains exactly the same.
Should I say all individuals are living in that point of time?
Yes, here.
Dying?
Here everybody is alive.
Yeah, they are still all living. They will die sometime, but we don't see when they die.
No, but this is, if we have a look at the group with highest intelligence, after 5,000 days, I don't know, 0.5% have died. You see? While at the same time period of those with the lowest, 2% have died. After 10,000 days, 6% in that group have died, 2% in that group. So of course this gives an indication how the survival looks in the different groups. I guess that might be a nice way to illustrate your results.
You should show what of them?
Well, this is more for, I guess this is mind-boggling. I guess most people, you just show it, oh, look, it's parallel, it looks fine. But this, of course, we can interpret, like we did, for descriptive information. How does it look? How does the survival look in the different groups? Okay, I think I stopped there. We can check for interactions. We can have time-dependent predictors. But we'll do this with computers, so I'll explain that. Okay. So, any questions? So let's have lunch.